So the model he proposed for the atom said that most of the atom was empty space and that there was a nucleus in the centre of the atom, and this contained a positive charge. The electrons orbited randomly around the nucleus. The first evidence that there might be a better model came from studying the ionization energy of atoms. The ionization energy is the amount of energy required to remove successive electrons from an atom. You can see from the graph that a small increase in energy is required to remove each electron, but occasionally there are big jumps in the energy, which indicates that there's something that makes it a bit harder to remove the next electron at certain points. So the story is a little bit more complex than just randomly orbiting electrons. The next evidence which contributed to our knowledge comes from the burning of compounds in a flame. For example, when copper carbonate burns, it emits a green light. If we analyse this light, we see it's actually composed of blue, green and white light. When we heat calcium carbonate in a similar way, it gives off orange-red light. Different elements give off different colours, so there must be some way of explaining why this actually occurs. When white light passes through a prism, it splits into a rainbow of colours. When light is emitted from a hot gas, as it passes through the prism, we see distinct lines. This is called an emission spectrum, and each element has a distinct spectrum. If, on the other hand, we pass light through a cold gas, then some of the energy is absorbed and we see what we call an absorption spectrum, which is almost the mirror image of the emission spectrum. Each element has a specific absorption spectrum and a specific emission. So what's going on? The suggestion was that the electrons were absorbing the heat energy and jumping to a higher energy level. The electrons wouldn't jump unless the energy was at exactly the right amount. When the electrons dropped back to the lower energy level, the extra energy was released in the form of light, which has a particular energy corresponding to the difference in energy between the two levels. The light emitted by the atoms has fixed energy, and hence it also has a fixed wavelength. Sometimes this can be in the UV region or the IR region, or else in the visible region. You can see from this diagram that drops from higher levels down to level 1 correspond to ultraviolet light, drops from higher levels down to level 3 involve infrared light, and drops down to level 2 involve the visible light. The ionization energies and the emission spectrum of the elements gave strong evidence for the existence of shells. So in 1913, Bohr proposed a model in which an atom had a central nucleus, but the electrons weren't orbiting in a random fashion like Rutherford believed, but were in distinct energy levels which he called shells. Bohr's model was worked out mathematically, and it had a set of rules. It stated that the electrons in each shell had the same energy, and that the number of electrons that could occupy each level was fixed, and it followed a set of rules. 2n squared, where n is the shell number, is the maximum number of electrons that can be held in each shell.
To work out electronic configuration, first we look at the atomic number, which gives us the number of electrons. In the case of phosphorus, that's 15. Then we start placing electrons in the lowest energy levels until they are full. So in shell 1 we can put 2 electrons, shell 2 will take 8, shell 3 will take 5, giving us a total of 15 electrons. For nickel, which has 28 electrons, first of all we place our 2 in the first shell, our 8 in the second shell, and in the third shell we put 8. However, it actually requires less energy to put an electron in the fourth shell than it does to add another electron to the third shell. So first of all we'll put 1 in shell 4, and in fact once we have 2 in the fourth shell, we can then go and backfill the third shell until we get up to our required 16, and that gives us our 28 electrons. Argon has a very similar situation. We start with 2 in the first shell, 8 in the second, and 8 in the third. Then we put our 2 into the fourth shell, go back and backfill our third shell up to 18. which means we now have a total of 30 electrons, and then we need to add the extra electrons to the fourth shell, giving us a total of 8 in that outer shell.
Bohr's model works extremely well for hydrogen, which only has one electron. However, when there are more electrons, the model falls down a bit. It can't explain the multitude of lines that are obtained when we use different elements which are a little bit heavier. So this is obviously not quite the end of the story. So now we have a nucleus with protons and neutrons. The number of protons determines what type of atom it is, and we call this the atomic number. So for example, carbon always has 6 protons, every calcium atom always has 20, and so on. In a neutral atom, the atomic number is also equal to the number of electrons. Now let's just change tack for a minute and concentrate a little bit more on the nucleus. If we pack all that positive charge into the nucleus, you'd expect there to be a bit of repulsion between the positive particles. So there must be something else there to stabilise the nucleus. In 1932, Chadwick proposed the existence of neutrons, particles with no charge which also resided in the nucleus and helped contribute to the mass. Since the electrons are very small, most of the mass is determined by the protons and neutrons. The total number of protons and neutrons is called the mass number. Although the number of protons is fixed for an element, it is possible for atoms to have a different number of neutrons, and these atoms are called isotopes of the particular element. You remember from last year that the isotopes can be represented using a Euclid symbol. The element symbol is given, and the number at the bottom is the atomic number, the number of protons, and the top number is the mass number, the total number of protons and neutrons. Of course, we can always calculate the number of neutrons by just subtracting the atomic number from the mass number. Many elements have several isotopes of their atoms, and the abundance of these varies. Carbon has 3 isotopes, with the major one being carbon-12. Chlorine has 2 isotopes in roughly equal proportions, while lead has 4 stable isotopes. Some elements have radioactive isotopes which are not stable and break up, such as uranium. The half-life of this decay also varies from milliseconds to thousands of years. Just refreshing your memory from last year, you remember that if we remove an electron from an atom, often a metal, we create a positively charged ion called a cation. We can remove 1, 2 or 3 electrons depending on the atom. Likewise, if we add an electron to an atom, we create an anion which has a negative charge. This is most likely to happen with non-metals. And of course, when one atom loses electrons, another one gains them. Sodium loses 1 electron and becomes sodium plus, and fluorine gains 1 electron to become fluoride minus. And then the attraction between the positive and negative ions forms an ionic compound. But more of that later. So, have we solved the atomic structure issue? Not quite. If you look at the emission spectrum of other elements, there are multiple lines, and these can't be explained by the existence of just 4 or 5 shells. Likewise, if you look at the graph of ionization energy versus atomic number, you can see the big jumps corresponding to removing electrons from complete shells, but there are also mini jumps and unexplained dips in the graph which we still haven't explained. This led Schrödinger to postulate the wave model, where there are no distinct shells but more areas of charge density, where the probability of finding an electron is greater. Within these charge clouds are regions called orbitals, which determine the electron configuration of the atom. So we can see that most of the development of the atomic theory has happened in the last 200 years, and from many areas of the world simultaneously. Not a lot happened before 1800, but there's been a lot done since then. Summarising the models we've talked about so far, we can see the transition from the indivisible atoms postulated by Democritus right through to the wave model proposed by Schrödinger.